Formal statement, hypotheses, and conclusion. Let f and g be real-valued functions defined on a closed interval, a to b. The theorem requires both f and g are continuous on a to b. Both f and g are differentiable on the open interval, a to b. G' of x not equal to 0 for every x in the open interval a to b. This prevents division by 0 later. If these conditions hold, then there exists at least one point C belonging to the open interval a to b such that f' of c divided by g' of c equals f of b minus f of a divided by g of b minus g of a. In other words, the ratio of the instantaneous rates of change of f and g at c equals the ratio of their total changes over the whole interval. This is a two-function extension of the ordinary mean value theorem. A helpful real-world analogy. Imagine two cars traveling the same road from point A to point B. Car F records distance f, and car G records fuel consumption G. The theorem says that at some moment during the trip, the instantaneous fuel efficiency, change in distance per change in fuel, equals the overall average fuel efficiency for the whole trip. Explanation: proof using Rolle's theorem. Start with the same hypotheses as above. Define a new auxiliary function. H of x equals left bracket f of x minus f of a right bracket left bracket g of b minus g of a right bracket minus left bracket g of x minus g of a right bracket left bracket f of b minus f of a right bracket. Because f and g are continuous on a closed interval a comma b and differentiable on an open interval a comma b, the same is true for h. Evaluate at the endpoints. H of a equals 0 and h of b equals 0. Indeed, each bracket becomes 0 at x equals O or x equals b. Thus h satisfies the conditions of Rolle's theorem. Continuous on a closed interval, differentiable inside, and equal values at the endpoints. Therefore, there exists a c in the open interval, a comma b with h' of c equals 0. H' of x equals f' of x times left bracket g of b minus g of a right bracket minus g' of x times left bracket f of b minus f of a right bracket. F' of c times left bracket g of b minus g of a right bracket equals g' of c times left bracket f of b minus f of a right bracket. F' of c divided by g' of c equals f of b minus f of a divided by g of b minus g of a. Thus the theorem follows directly from Rolle's theorem. The proof can be visualized as tilting the graph of f until it aligns with the graph of g. The point where the tilt makes the two end differences match is the c guaranteed by Rolle. Derivation of L'Hopital's rule. L'Hopital's rule deals with limits of the indeterminate forms 0 over 0 or infinity over infinity. Suppose limit as x approaches of f of x equals 0 and limit as x approaches of g of x equals 0. And both functions are differentiable near or with g' of x not equal to 0 for x not equal to a. Consider the interval bracket x comma a bracket or bracket a comma x bracket if x greater than a. Applying Cauchy's mean value theorem on this tiny interval gives a point c between x and a such that f of x minus f of a divided by g of x minus g of a equals f' of c divided by g' of c. Since f of a equals g of a equals 0, the left-hand side simplifies to f of x over g of x as x approaches a. The point c also approaches a by the squeeze theorem. If the limit as t approaches of f' of t over g' of t exists, finite or plus or minus infinity, then letting x approach a yields. Limit as x approaches of f of x over g of x equals limit as c approaches of f' of c over g' of c. This is exactly L'Hopital's rule for the 0 over 0 case. The same reasoning works for the infinity over infinity case after subtracting a large constant or using reciprocal functions. In plain language, Cauchy's theorem guarantees a point where the instantaneous rate ratio equals the average ratio over a tiny segment. As the segment shrinks to a point, the average ratio becomes the limit we seek, and the instantaneous ratio becomes the ratio of derivatives. For a real-world picture, think of two water tanks being emptied simultaneously. When both have almost no water left, the 0 over 0 situation, the ratio of how fast the water level drops is given by the ratio of the flow rates at some instant just before they empty. That instant is the c supplied by Cauchy's theorem. Picture the graphs of y equals f of x and y equals g of x on the same set of axes. Draw the secant line joining the points a, f of a and b, f of b. Its slope is f of b minus f of a divided by b minus a. Do the same for g. Cauchy's theorem says there is a c where the tangent to the curve f and the tangent to the curve g are not parallel to the x-axis, but point in exactly the same direction when you consider the vector f prime of c, g prime of c. In other words, the line through c, f of c with slope f prime of c, and the line through c, g of c with slope g prime of c form the same angle with the x-axis. A useful visualization. Construct the combined curve h of x equals f of x minus lambda g of x, where lambda equals f of b minus f of a divided by g of b minus g of a. The secant slopes of f and g make the combined curve have equal values at a and b. That is h of a equals h of b. Rolle's theorem tells us there is a point where h prime of c equals 0, meaning f prime of c equals lambda g prime of c. Geometrically, the tangent to h at c is horizontal. The tangents to f and g at the same x-coordinate have slopes that satisfy the ratio relation. Analogy: imagine two hikers walking up different hills, starting together at point A and ending together at point B. Their overall change in altitude over the whole trip, the secant slope, might differ. But Cauchy's theorem guarantees a moment when the instantaneous steepness of each hill measured at the same horizontal position is in the same proportion as their total altitude gains. A simple diagram drawn on paper would have the two curves crossing the vertical strip A to B. Two secant lines, one for each curve, colored differently. A vertical line at x equals c showing the two tangent lines whose slopes satisfy the ratio. This picture makes it clear why the theorem is a natural generalization of the ordinary mean value theorem, where g of x equals x, and the secant of g has slope 1. Problem: let f of x equals ln of x, and g of x equals x on the interval 1 to e. Verify the hypotheses of Cauchy's mean value theorem, and find a point c in 1 to e that satisfies the theorem. Step 1. Check continuity. Both ln of x and x are continuous on 1 to e. Step 2. Check differentiability. Both are differentiable on open interval 1 to e with derivatives f prime of x equals 1 over x and g prime of x equals 1. Step 3. Check g prime of x not equal to 0. Indeed, g prime of x equals 1 never vanishes. Step 4. Apply Cauchy's formula. F prime of c divided by g prime of c equals open parenthesis f of e minus f of 1 close parenthesis divided by open parenthesis g of e minus g of 1 close parenthesis. Compute the right-hand side. F of e minus f of 1 equals ln of e minus ln of 1 equals 1 minus 0 equals 1, and g of e minus g of 1 equals e minus 1. Hence 1 over c divided by 1 equals 1 over e minus 1, which gives 1 over c equals 1 over e minus 1. Solving gives c equals e minus 1. Step 5. Verify that c lies inside the interval. E approximately 2.718, so e minus 1 approximately 1.718, which indeed belongs to open interval 1 to e. Thus the required point is c equals e minus 1. The answer shows the theorem in action. The ratio of the instantaneous rates 1 over c and 1 matches the ratio of the total changes over the interval. Exam tip: always write down the 3 hypotheses first. Then compute the right-hand side, the secant ratio, and solve the equation f prime of c divided by g prime of c equals that ratio for c if multiple solutions appear. Pick the one that lies strictly inside the open interval. Explanation: application to inequalities and monotonicity. Cauchy's theorem is a powerful tool for proving statements like if f prime of x divided by g prime of x is increasing, then f of x minus f of a divided by g of x minus g of o is also increasing. If f and g satisfy certain sign conditions, the ratio f of x divided by g of x inherits monotonicity. Key idea: the theorem links a local ratio, derivatives at a point, to a global ratio, differences over the whole interval. By varying the endpoint b and applying the theorem repeatedly, one can compare two ratios. Example - proving an inequality: let 0 less than b and consider f of x equals natural log of x, g of x equals x minus 1. For x greater than 0, we have f prime of x equals 1 over x, and g prime of x equals 1. Since 1 over x is decreasing, the ratio f prime of x divided by g prime of x equals 1 over x is decreasing. Cauchy's theorem then tells us that the secant ratio natural log of b minus natural log of a divided by b minus a is also decreasing as a moves rightward. This yields the classic inequality. The natural log of b minus natural log of a divided by b minus a is less than or equal to 1 over a, which after rearrangement becomes natural log of b minus natural log of a is less than or equal to b minus a over a. Monotonicity of a ratio : suppose f and g are differentiable on the interval from a to infinity with g prime of x greater than 0, and the ratio f prime of x divided by g prime of x is non-decreasing. Define r of x equals f of x minus f of a divided by g of x minus g of a. For any x greater than y greater than a, apply Cauchy's theorem on the interval from y to x to get a point C in the interval y to x with r of x minus r of y equals f prime of c divided by g prime of c minus f prime of d divided by g prime of d, where d is in the interval y to x from the other subinterval. Because the derivative ratio is non-decreasing, the right-hand side is greater than or equal to 0. Hence, r of x is greater than or equal to r of y, proving that r is monotone. Real-world analogy : think of two production lines, one producing widgets F and the other producing raw material G. If the instantaneous efficiency ratio, widgets per raw unit, never drops, then the average efficiency over any longer period also never drops. Cauchy's theorem formalizes exactly this intuition. Problem: apply Cauchy's mean value theorem to f of x equals sine x and g of x equals x on the interval from 0 to pi. Find a point C that satisfies the theorem and interpret the result. Step 1. Continuity and differentiability. Both sine x and x are continuous on the interval from 0 to pi and differentiable on the open interval from 0 to pi. Step 2. Check that g prime of x is not equal to 0. Here g prime of x equals 1, never 0. Step 3. Compute the secant ratio. F of pi minus f of 0 divided by g of pi minus g of 0 equals sine pi minus sine 0 over pi minus 0, which simplifies to 0 minus 0 over pi equals 0. Step 4. Set up Cauchy's equation. F prime of c divided by g prime of c equals 0, which gives cosine c over 1 equals 0. Hence cosine c equals 0. Step 5. Solve for c in the interval from 0 to pi. The cosine function is 0 at c equals pi over 2. Step 6. Verification. C equals pi over 2 indeed lies inside the interval. Interpretation. The average change of sine x over the interval from 0 to pi is 0 because the sine curve goes up then down, ending at the same height. Cauchy's theorem tells us there is a point where the instantaneous rate of change of sine, which is its derivative cosine, is also 0. That point is the peak of the sine wave at pi over 2. Extension: if we choose a different interval, say from 0 to pi over 4, the secant ratio would be sine pi over 4 minus 0 divided by pi over 4, which equals square root of 2 divided by 2 over pi over 4, simplifying to 2 times square root of 2 over pi. Solving cosine c equals 2 times square root of 2 over pi gives a different c inside the interval, illustrating how the theorem adapts to any subinterval. Practical analogy: imagine a Ferris wheel completing half a turn from the bottom to the top and back to the bottom like the sine wave. The net vertical displacement is 0. The theorem guarantees there is a moment when the vertical speed is exactly 0, the instant the wheel reaches the top. Check hypotheses. Both functions are continuous on 0 to 1 and differentiable on 0 to 1 open. Also, g prime of x equals 2x is 0 only at x equals 0, but the theorem requires g prime of x not equal 0 on the open interval. However, we can restrict to 0 to 1 closed on the right and note that any c given by the theorem must be greater than 0, so the condition holds. Apply Cauchy's theorem. Compute the right-hand side. F of 1 minus f of 0 equals e minus 1, g of 1 minus g of 0 equals 2. Hence, the secant ratio is open parentheses e minus 1 close parentheses divided by 2. Set the derivative ratio equal to this value. F prime of c over g prime of c equals e to the c divided by open parentheses 2c close parentheses equals open parentheses e minus 1 close parentheses divided by 2, which implies e to the c equals c times open parentheses e minus 1 close parentheses. The equation e to the c equals c times e minus 1 has a unique solution in 0 to 1. One can argue by monotonicity of the left-hand side and right-hand side. Denote this solution by C0. Monotonicity of the ratio. Define r of x equals e to the x divided by open parentheses x squared plus 1 close parentheses. Its derivative is r prime of x equals open bracket e to the x times open parentheses x squared plus 1 close parentheses minus e to the x times 2x close bracket divided by open parentheses x squared plus 1 close parentheses squared. This simplifies to e to the x times open parentheses x squared minus 2x plus 1 close parentheses over open parentheses x squared plus 1 close parentheses squared, which further simplifies to e to the x times open parentheses x minus 1 close parentheses squared over open parentheses x squared plus 1 close parentheses squared, greater than or equal to 0. Since the numerator e to the x times open parentheses x minus 1 close parentheses squared is always non-negative and 0 only at x equals 1, we see that r prime of x is greater than or equal to 0 on 0 to 1. Therefore, r is non-decreasing. In fact, it is strictly increasing on 0 to 1 open interval. Connection with Cauchy's point. The value of C0 obtained from the theorem is precisely where the instantaneous ratio of the derivatives matches the overall change. Because r prime of x is greater than or equal to 0 everywhere, the ratio r of x never decreases, confirming the monotonicity conclusion. Key takeaway for exams: verify the hypotheses carefully, especially g prime not equals 0. Use the theorem to locate a special point, then differentiate the ratio directly to decide monotonicity. The combination of the theorem and derivative test often earns full credit. Exam tip: if g prime of x vanishes at an endpoint only, the theorem is still applicable because the required c will lie inside the interval where g prime is not equals 0. State this explicitly to avoid loss of marks. Comparison with the ordinary mean value theorem and guidelines. Feature ordinary mean value theorem, Cauchy's mean value theorem. Functions involved: one function f, two functions f and g. Typical hypothesis: continuous on a closed interval a comma b, differentiable on an open interval a to b, continuous for both on a closed interval a comma b, differentiable for both on an open interval a to b, and g prime of x not equal to 0 on an open interval a to b. Conclusion: there exists a c such that f prime of c equals f of b minus f of a divided by b minus a. There exists a c such that f prime of c divided by g prime of c equals f of b minus f of a divided by g of b minus g. Geometric view: tangent to f is parallel to the secant of f. Tangent to f and g have the same direction, their slope ratio matches the secant ratio. Common uses: proving increase or decrease, estimating errors, proving inequalities for ratios, L'Hopital's rule, monotonicity of f over g. Only one function appears, use the ordinary mean value theorem. Example: show there is a point where f prime of c equals 0 for a function that has equal values at the ends. You need a relation between two functions. If the problem asks about the ratio f of x over g of x, or involves expressions like f of b minus f of a and g of b minus g of a together, think of Cauchy's mean value theorem. L'Hopital's rule: the classic derivation begins with Cauchy's mean value theorem. So any limit of the form 0 over 0 or infinity over infinity should trigger the Cauchy version. Inequality of averages: when you want to compare f of b minus f of a divided by g of b minus g of a with f prime of x divided by g prime of x for some x inside, Cauchy's mean value theorem is the direct tool. If g prime of x may vanish, check the interval carefully. If it only vanishes at an endpoint, Cauchy's mean value theorem can still be applied. Otherwise, you must modify the interval or choose a different technique. Practical tip: write a short checklist on your scratch paper before starting a proof. Continuity of all functions on a closed interval a comma b, differentiability on an open interval a to b. Is g prime of x never 0 inside? Compute the secant ratio, f of b minus f of a divided by g of b minus g of a. Solve f prime of c divided by g prime of c equals that ratio for c. If everything checks out, you have the Cauchy point. Analogy for selection: think of the mean value theorem as a single-engine airplane that tells you there is a moment when the speed equals the average speed. Cauchy's mean value theorem is a twin-engine aircraft. It tells you that both engines, two functions, align their thrust to fuel consumption ratios at some instant. When the problem involves fuel efficiency, a ratio, you need the twin engine version.